Hello everyone. This presentation is mostly discussed on the topic of the memory management in the real-time operating system. As clearly shown in the slide, memory allocations. First of all, we have to discuss about the memory management. What is the need of the memory management? Embedded system developers commonly implement custom memory management facilities on top of what the underlying real-time operating system provides. Understanding memory management is therefore an important aspect of developing for embedded system. Knowing the capability of the memory management system can aid application design and help avoid pitfalls. And these are the following three types of the memory management. We are classifying in this slide. Memory managing a strategy for a system, first of all, is the fixed block allocation, and then the dynamic page allocation, and the third one is the dynamic data memory allocation. Now, RTOS system mainly focus on the dynamic data memory allocation. Dynamic memory allocation in embedded system. As shown in the previous slide, we have to study on in the previous chapter also about the program code, program data, and system stack occupy in the superficial and superficial knowledge in the courses study. Occupy the physical memory after program initialization completes. Either the RTOS or the kernel typically uses the remaining physical memory for dynamic memory allocation. This memory area is called the heap. Memory management in the context of this chapter refers to the management of a contiguous block of a physical memory. Although the concept introduced in this presentation apply to the management of the non-contiguous memory blocks as well, with the following example. This is the example for the memory fragmentation and compactness. In this example implementation, the heap is broken into a small fixed size blocks. Each block has a unit size that is power of 2 to easy translating a requested size into the corresponding required number of units. It is clearly shown in this figure as an example. The heap is the 25/6 bits. The unit size is 32 bytes. The dynamic memory allocation function malloc has an input parameters that specifies the size of the allocation request in bytes. Malloc allocates a larger block which is made up of one or more of the smaller fixed size blocks. The size of this larger block, memory block, is at least as large as the requested size. It is the closest to the multiple of the unit size. For example, as shown in this slide, if the allocation requests 100 bytes, the return block has a size of 128 bytes. That is corresponds to the 4 units of each 32 bytes per unit. As a result, the requester does not use 28 bytes of the allocated memory, which is called memory fragmentation. And the next slide we have to discuss about the memory compaction continues until all the free blocks are combined in a one large chunk. It is a clear shown in this figure and this slide. Another example of the state of an allocation table. In this slide, it is note that two free 32 bytes blocks are shown. One block is at addresses 0 cross 10080 and the other at address 0 cross 101030, which cannot be used for any memory allocation request larger than 32 bytes. Because these isolated blocks do not contribute to the contiguous free space needed for a large allocation request. That's their existence makes it more likely that a large request will fall or take too long. The existence of these two trapped blocks is considered external fragmentation because the fragmentation exists in the table not within the block themselves. One way to eliminate this type of fragmentation is to compact the area adjacent to these two blocks. Clear? Next slides we have to focus on the fixed site memory management in embedded system. In this slide we have to discuss about the another approach to memory management uses the method of fixed site memory pools. This approach is commonly found in embedded networking code such as an embedded protocol stacks implementation. As clearly shown in this figure, the available memory space is divided into variously sized memory pools. All blocks of the same memory pool have the same size. In this example, the memory space is divided into three pools of block size 32, 50 and 128 respectively. Each memory pool control structure maintains information such as the block size, the total number of blocks and the number of free blocks. It is clear shown in this example. Memory pools are linked together and sorted by size. Finding the smallest size adequate for allocation requires searching through this link and examining each control structure for the first adequate block size. That is the brief structure of the memory management in this presentation. Thank you.